and that is the rarefaction. You can see the alternate compression and rarefaction, compression, rarefaction, compression, rarefaction. It will pass the disturbance which is created at the place of source, and that disturbance is traveling along the path by the particles of that membrane or the particles of that medium, and those traveling is in the form of compression of particles, the place of higher density where particles come together, and the rarefaction, the medium in which particles go away from each other or the at the normal position. So sound is propagated in the form of compression and rarefaction. And the next concept, the whole sound is traveling in the form of two waves. There are two types of waves. First was the longitudinal wave and the second was the transverse waves. What is the difference between longitudinal waves and transverse waves? The longitudinal waves, the particles in that medium oscillate about their central or the mean position, but their oscillation is parallel to the direction of propagation, in which when sound is that disturbance is traveling in this direction, the particles will do compression, rarefaction, compression, rarefaction, compression, rarefaction, and the particles will move forward and again move backward. That will be the position of particles of medium which are traveling parallel to the propagation of sound. So if the sound propagate in this way, the particle will move forward and again move backward. That will be the parallel movement. So in longitudinal waves, the particles oscillate about their central position or mean position parallel to the propagation of sound, and exactly opposite in transverse waves. If the propagation of sound is in this direction, the particles will move upward and downward. That is exactly perpendicular to the propagation of sound. So in transverse waves, the type of waves in which the particles of the medium oscillate about their central or the mean position in their direction perpendicular to the propagation of the wave, and this is called as a transverse wave. So we have seen different terminologies. First was the lambda, which is called as a wavelength sound source, and this is the central or the mean position. Sound wave is this, and the lambda, that is wavelength, length of the wave. It is the distance between two grooves, two ridges or two furrows. That is called wavelength of sound. Next, frequency of sound, that is nu. If the disturbance traveling through any medium is pass rapidly, the frequency will be more. If it is slow, then the frequency, number of time the ridges is forming, that is frequency. Next, amplitude. We have seen amplitude, the source, mean position, and the length of the wave, length of that ridge or the furrow, that will be the amplitude. That is calculated through this. Next, we have still time period, the particular disturbance which is traveling from the source of the sound to particular position in particular time, that time period is calculated. That is called time period, capital T. Then we have seen pitch and we have seen loudness. Then we have seen velocity of sound is equal to frequency into wavelength. How velocity of sound is calculated, the frequency into wavelength. And today we are going to cover the physical conditions which are affecting on velocity of sound. Then we will see the types of sound, which are the types of sound. Then we will see how sound is reflecting on the different surfaces. Then we will see which are the good and bad reflectors of sound. Now we will first see the velocity of sound in gaseous medium. It is dependent on different physical conditions. The velocity of sound in gaseous medium, that is air, it it is dependent on different physical conditions. Physical conditions means atmospheric conditions. There, the temperature, the density of gas, and the molecular weight of that gas. So these are the three conditions we are going to see in which are affecting velocity of sound in gaseous medium. The first one is temperature, capital T. The statement is the velocity of sound is directly proportional to the square root of temperature of the medium. Velocity of sound, that is V, is directly proportional to the square root of temperature. The velocity of sound is V and it is directly proportional. What this sign, directly proportional, inversely proportional, what does that sign means? Can anybody have guess? I will explain in detail. Okay, the direct proportional, first we will see direct proportion and then we will see inverse proportion. Inverse proportion. Okay, so direct proportion. Now, first example, that is price of vegetable. Price of vegetable. Now, day by day, the price of vegetable is increasing. It is dependent on petrol. If I am considering petrol, if I am increasing the value of petrol per liter, then automatically the vegetable vendors which are getting those vegetables will increase their values. So the petrol and price of petrol and price of vegetables are in the direct proportion. If I am increasing one value, there will increase in another value. That is called as a direct proportion. So in the next point, inverse proportion, what do you mean by inverse proportion? In inverse proportion, if I am increasing one value, there will be decrease in another value. Okay. For example, if I am giving 2 days, if I am giving 2 days, and these 2 days from day one, you have given 8 lessons to study. So day one will start, day one will complete. You have finished 4 lessons. Day two will start. You will complete all lessons. So day one, the day are increasing, and the syllabus, that is 8 lesson, from 8 lesson there is a decrease in one lesson, so the second value is decreasing, so it will be in inverse proportion. Both the values are in inverse proportion. Okay, so if velocity temperature is increasing, then the velocity will also increase, because both are in direct proportion. But the velocity of sound is directly proportional to the square root of temperature. So direct proportion, but the square root. So this means that if a temperature, if I increase temperature 4 times, if I increasing temperature 4 times, there will be increase in velocity by 2 times. There will be increase in velocity of sound by 2 times. It will double, not 4 times. Temperature we have increased 4 times, but the velocity will increase 2 times, because there is a square root. There is a square root given. Next, the second physical state, that is second condition, which is affecting on atmosphere velocity of sound, is density. So the statement is given: the velocity of sound is inversely proportional to the square root of the density. So again, square root is there, but the density is inversely proportional to the velocity of sound. If we increase the density, if we increase the density by 4 times, there will be half increase, half reduction in velocity. So velocity will decrease by half. Next, the next concept or the next factor which is affecting velocity of sound in air or in any gas, the molecular weight of that gas will affect in this way. The statement: the velocity of sound is inversely proportional to the square root of molecular weight of the gas. So again, square root is there, but the molecular weight and the velocity of sound in gaseous medium are both in inverse proportion. So again, inverse proportion says that if the molecular weight is increasing, velocity of sound will decrease. You have to keep in mind this logic, so that you will understand: when molecular weight is increasing, velocity of sound will decrease. If molecular weight is decreasing, the velocity of sound will increase. But how, in what proportion there will be increase or decrease in velocity of sound is there? The statement is given: the velocity of sound is inversely proportional to the square root of molecular weight of the gas. So it it clearly says that if I'm increasing the molecular weight by 4 times, there will be reduction of velocity of sound into its half of the value. So if agar there will be increasing 4 times, the value of increase 4 times, the square root of 4 is equal to 2, and therefore there will be reduction, value will be reduced by half. Simple calculation, you can um, keep in mind this calculation. Now the next concept, that is types of sound. The sound is of 3 types. First, which is audible to our ears. Our ears can listen only 20 hertz to 20,000 hertz. The frequency between 20 to 20,000 hertz will be audible to your ears. Beyond this, larger than this, greater than this, and smaller than this. The both frequencies we can't hear through our ears. Therefore, we have earphone, therefore we have mobiles, therefore we have some instruments using which are using these lower frequencies, higher frequencies to convert into your audible range, so that you can analyze, you can find out what is the difference between both the sounds. So audible range of our ears is 20 hertz to 20,000 hertz. That is the frequency unit. Hertz, that is frequency unit. So our ears can't hear infrasound. So now I'm talking with you. I'm A. If I'm A person, just a second. Okay, that will be more enough. I'm A person. I'm talking with my mobile. So my mobile is connected with tower, and the tower is connected with our satellites, and satellite is again connected with our tower, and tower is connected to your mobile, that is B. Okay. Now I am talking between 20 to 20,000 hertz. Okay, 20,000 hertz. I'm talking in 20,000 hertz, 20 to 20,000 hertz. You are listening, you are listening between these frequency, but the traveling of rays, the traveling of this ray is lower than this. So my mobile will convert that electrical impulse into lower frequency, and this is passed through the tower, and tower into the satellite, satellite again connected, connection will be there, and your mobile will convert that lower frequency to again 20 to 20,000 hertz, and that will done in your mobile. Now uh, we have seen, we are going to see the different frequencies and how these different frequencies are used in different instrument for our useful use, to use the different instruments. The limit of our hearing is very low, that is 20 to 20,000 hertz, and you can increase that hearing with your meditation, with your daily activities. Okay. This, the human ear can hear up to the frequency between 20 to 20,000 hertz range. These sounds are called as a audible sounds, and our ears cannot hear the sound frequencies lower than 20 hertz and higher than 20,000 hertz. The 1 hertz is equal to 1 kilohertz is equal to 1,000 hertz. Therefore 20,000 hertz means 20 kilohertz. So a conversion, you have to keep in mind this conversion. 1 kilohertz is equal to 1,000 hertz. You have to keep in mind this conversion. So the frequency that is higher than 20,000 hertz or the 20 hertz will not be heard by our ears. We can't hear that frequency. Sound with the frequency also smaller than the 20 hertz will also be not audible to our ears. So you have your mobile is having different radio stations, and that radio station, the name radio itself is showing that these waves are in the form of radio waves or the infrareds. These infrareds are traveling from atmosphere, and they are having frequency smaller than the audible range. So there are some examples: sound produced by pendulum, sound generated by vibrations of earth before earthquake. These are the some examples of infrared or infrasound. The dog, mouse, bat, dolphin, these are the some, these are having some spatial ability to hear that infra radiations or infrasound. The kid under our if your house has the kid which is smaller or under the 5 years age, that kid will also hear up to 25 kilohertz. That children, that child will hear. We have that much efficiency, but we lost it in the in our day-to-day life. The insect, some creatures will also hear the frequency up to 25 kilohertz. We can't. The sound waves with frequency greater than 20 hertz, 20 kilohertz, that is 20,000 hertz, are called as a ultrasound. There are some examples. The bat, it can produce ultrasonic sound and travel in the dark. The mice can also produce ultrasonic sound and it can do their work. Dolphins in the water, it can produce the ultrasonic sound and it will also survive. There is a range between 10 to 20,000 hertz, and above that range there is a ultrasonic sound. There is a ultrasonic sound above range, that is the 20 to 20,000 hertz, that is. And below is infrasonic sounds. There are some examples also given. Bat, when 2 kilohertz to 120 kilohertz. Dolphin, insect, rat, bird, frog and toad, they have 50 hertz to 4 kilohertz. Crocodile, dog, elephant, blue whale. These are some examples. Everyone has this ability to hear sound, whether they have ears, specified ears or not. They can collect or they can receive the message which is forwarded in this frequency. In that frequency, no need to have specified ears to listen. So frequency, we can detect that frequency. Someone is looking at me, is identified my organs, identified my bodies due to different waves which cannot be uh, I can't detect that, but my body will detect that someone is looking at me, someone is asking about me, and someone is thinking about me. That can be, it is visualized, it is all through the waves which are infra radiations, ultrasonic sounds. So sound is our life of part of life. So there should be reflection of sound. Someone is asking to you, someone is speaking with you, and if we are there as like reflection of light, there is a reflection of sound also. So the sound reflects in the same manner as like a light reflects. There is one beautiful video for you. Just enjoy that video.
Sound is a part of our everyday sensory experience. So, how is sound produced, propagated, and detected? A good model is the stethoscope, used to listen to the sounds of heart and lungs. But how are these sounds heard? To understand this, we need to know what reflection of sound is. When sound travels through a medium, It strikes the surface of another medium and bounces back to the original medium. This phenomenon is called the reflection of sound, which obeys the laws of reflection. The first law states that the angle of incidence is equal to the angle of reflection. We can provide this by placing two tubes at certain angles on a wooden board. If a clock is placed near the end of one of the tubes, we can hear the sound waves through the second tube by adjusting it to get the sound at its maximum. We can see that the angle of incidence is equal to the angle of reflection. The second law states that the incident wave, the reflected wave, and the normal at the point of incidence all lie in the same plane. Sound waves also suffer reflection from large obstacles. If we stand at a distance from a high wall and clap our hands, we can hear the same clapping sound after the dying out of the original sound. This is called an echo. Therefore, for an echo to be heard, the time interval between two sounds must be 0.1 seconds. As sound travels at a speed of 340 meters per second in air, the distance traveled by sound in 0.1 seconds is 34 meters. Therefore, to hear an echo, we need to stand at least 17 meters away from the wall. Now, what happens if there are four enclosed walls that are less than 17 meters away? What we experience here is a reverberation that is due to multiple reflections of sound from the walls, roof, and floor, which follow so closely behind the original sound that the original sound appears to be prolonged even when the source of the sound stops. We can thus say that reverberation is the multiple reflections of sound waves, whereas echo is the single reflection of sound waves. However, excessive reverberation makes the sound indistinct, which can be a setback in auditoriums. This can be reduced by using sound-absorbing materials like ceilings made of soft and textured materials and flooring made of acoustic tiles. Certain technologies make use of the multiple reflections of sound. To name a few, we have megaphones, hearing aids, soundboards, stethoscopes, and the curved ceiling of concert halls. Now, back to our stethoscope. The stethoscope picks up multiple reflections of sound from the patient's body. This causes the flat surface of the diaphragm to vibrate. Each wave bounces or reflects off the inside walls of the rubber tube. In this way, each wave in succession reaches the ear tips on the ends of the device and finally to the listener's eardrums, and the doctor interprets the sound he hears. Things to remember. The property of sound to bounce back from the surface on which it falls is known as the reflection of sound. Echo is heard only if the minimum distance between the source of sound and the obstacle is 17 meters. Reverberation is multiple reflections of sound after the original sound is produced. The first law of reflection states that the angle of incidence is equal to the angle of reflection. The second law states that the incident wave, the reflected wave, and the normal at the point of incidence all lie in the same plane.
I think you have enjoyed this video, especially for you. The light waves are traveling and they are reflecting from the surface. Like that, the sound waves also get reflected from the solid as well as the liquid surface. There are some rules. The first rule is, if this is the surface, sound waves are traveling, it is incident on particular surface at particular point, then at that point, if we draw perpendicular, that will be the normal. If This is the normal. This is the incident ray. Incident ray with normal is doing a angle of incident angle I. So after reflection from that point, the ray is called as a reflected ray, and that reflected ray will again do the angle, make an angle of angle R with a normal. So the law of reflection says that angle I is equal to angle R. That is the first rule. The second rule, which is says that the normal, incident ray, and the reflected ray, but three of them are in equal plane. They are in the same plane. They are in the same plane. Okay, these were the rules. Though these sound waves follow those laws of reflection, and the smooth or the rough surface, it will be required for sound to reflect. Now, the direction of incident sound wave and the reflected sound wave make equal angle with perpendicular to the surface of the surface, and all these are in the same plane as we have seen. So this is the picture. So this is the surface of the wooden board. If it is not visible, I will make it red. This is the surface of the wooden board, and if that is the normal for uh, getting incident ray and the reflected ray, we can hear that sound at a particular point. That angle, that is angle I and angle R, are equal, and both incident ray and reflected ray, and also the normal, third one is the normal, are in the same plane, are in the same plane. Now we are going to see the next concept, the reflectors of sound. How will you detect whether that reflector is good reflector or bad reflector, or whether that surface is not reflector? So in your textbook there are the good and bad reflectors of sound. So we will classify them according to this, that how much of the incident sound is getting reflected will decide whether that reflector is good or bad. So if that reflector is reflecting 100%, that will be the good reflector, and if that reflector is not not reflecting the 100% and 90%, though that will be the bad reflector. So that will be the good absorber also. The hard and the flat surface will be the good reflector. But if we see in the auditorium, in the theaters, the cloths are there, paper curtains are there, carpet is there, there is a absorbing cushion material. If we see the chairs also, they are with cushion, and if we see that theater, it will be also luxurious type, but that luxury is for only to absorb the sound. If the sound, there are speakers, uh, 2 3 speakers, if there are 2 3 speakers, the speakers will produce the sound, same sound. The sound will come to your ears. If that sound is reflected, then we can't hear that voice clearly. To listen that voice clearly, if there is one speaker, there is another speaker, the third one is here, fourth one is here, and fifth one is here, and you are sitting in here, the sound will directly come to your ears. First one. Second one will reflect to the surface and come to yours. The third one again, like this, all sound will produce, and all sound will reflect in that room. If the reflection is stopped, there will be no second round, second sound will not created, the second sound will not reach to your ears, so you will get clear sound of that movie and you can enjoy that movie. So these are the bad reflectors. They are good absorbers. Paper, curtains, carpets, different furnitures. These are absorbing the sound instead of reflecting that, and therefore they are called as a bad reflectors. There is a picture which is showing that the clothes, paper, curtains are there, and different material which is not reflecting, only absorbing, that will be considered as the bad reflector. So, in the last, we will see what do you mean by what is the relation between the temperature and the velocity of sound. So, the temperature, if we increase the temperature, there will be increase in velocity of sound. Just now we have seen, that is, the velocity of sound is directly proportional to the temperature, square root of temperature. So increasing temperature by 4 times will doubles the velocity of sound. Now the second question is that the what is the relation between the density of atmosphere or density of any that gas with the velocity of sound. So again, density of that gas or the density of atmosphere uh, in which the sound is traveling will be inversely proportional to the velocity of sound. So sound will reduce when density will be increased. So it will be inverse proportion. We have seen direct proportion and inverse proportion just now. So if we increase the density, there will be decrease in velocity of sound, and if we decrease this density, there will be increase in velocity of sound. But the proportion, they said that the velocity of sound is inversely proportional to the square root of that densities. There should be square root, means if we increase 4 times the density, if we increase density 4 times, there will be reduction in the velocity of sound with the half. The speed will be half. Next question, the what is the relation of molecular weight with the velocity of sound? So just now we have seen molecular weight if is inversely proportional to the square root of molecular weight, the velocity of sound is inversely proportional to the square root of molecular weight. Therefore the inverse proportional shows that if the molecular weight is increased, the velocity of sound will decrease. So, and if the molecular weight is decreasing, velocity of sound will increase. That is called as the inverse proportion. Just now we have seen, but that inverse proportional will be in this way, that the increasing molecular weight 4 times, if I'm increasing the molecular weight by 4 times, there will be reduction, half reduction in the velocity of sound. If we decrease 4 times, there will be increase in the half, it will increase. So next question, which are the types of sound? So types of sound, we have seen there are 3 types of sound. First, that is audible, infrared, infrasound, audible sound, and ultrasound. Infrasound having frequency lower than 20 hertz. Audible sound, that is frequency of this audible sound is 20 hertz to 20,000 hertz. We have seen that there is a conversion of 20,000 hertz, that is 20 kilohertz, and the sound which is greater frequency, having greater frequency more than 20 kilohertz, that is 20,000 hertz, it will be said as a ultrasonic sound, that is ultrasonic sound. So this audible sound is again, it is audible to only human being. Human ear can hear the sound which is having frequency 20 hertz to 20,000 hertz. Below that frequency, that is the lower frequency, that is infrasound, and it is only audible to the human being having age more less than 5 years, that is small kid which can hear that frequency, which can sense that frequency. We also have that ability, but not our ears, but our body can hear that lower frequency also. If we maintain our body like in that way, we can do that also. Next, what is the frequency of audible sound? Audible sound, the frequency of audible sound is 20 to 20,000 hertz. 20 to 20,000 hertz, that will be the audible frequency, which is frequency of human ear. And the frequency of infrasound, that is frequency of infrasound, is lower than 20 hertz. Below 20 hertz, the frequency is called as a infrasound. Next, the frequency of ultrasound is greater than 20,000 hertz, that is 20 kilohertz. Beyond 20 kilohertz and greater than 20 kilohertz, that is beyond 20,000 hertz or greater than 20,000 hertz, the frequency is called as a ultrasonic sound, that is ultrasound. Now, the next concept or the next question is, a reflection of sound follows which rules? The reflection of sound follows the rules of laws of reflection by light. So the first rule was that the incident angle, the angle which is made by incident ray with normal, is called as the incident angle, and angle made by reflected ray is with the normal is called as a angle of reflection, and that is r, small r. That angle I and angle r both should be equal. So that was the first rule. Second rule was the incident ray, reflected ray, and the normal will be in the same plane. That were the rules. Okay. And how do we classify the good or the bad reflector? The good and the bad reflectors are classified on the basis of their reflecting capacity. The hard and the flat surface are the best good reflectors. The clothes, curtains, papers, furnitures, these can absorb the sound, therefore they are considered to be bad reflectors. So therefore you are hearing very nice sound if the quality of that sound will be dependent on this reflecting capacity. So frequency will decide whether that sound is clear. Thank you, student. Okay, in a next lecture, we will see the next part of the examples of lesson number 12, the study of sound. Okay, thank you.
I think students now our fourth lecture has also ended.